Okay, well, going on with our discussion about the solving differential equations using a method of separation of variables to solve some simple differential equations, let's ask the state. What does the statement mean? The rate of change of y is proportional to itself. Now, it may seem like a strange statement to make, but in fact, this is the statement that essentially started it all when you think about it, because this is the statement that tells us about, for example, gravity. That the acceleration due to gravity can be proportional to itself, or some other rates of change are proportional to itself, especially when we think about things like population growth, radioactive decay, bank account interest. There's all kinds of applications for what this statement might mean, but what does it mean itself? Well, what would we say? Well, let's look into this. Remember that we know the statement that if A is proportional to B, then A is equal to some constant times B. So how could we use that? Well, interestingly, what we're going to do right here is we're going to say, well, if that's the case, then if y is proportional to if the rate of change of y, let's say that y is changing with respect to time t. Well, that means that the rate of change of y with respect to t is proportional to itself, so it's some constant times itself, times y. And this is actually the kind of equation that we know how to solve by our separation of variables, because kind of like what we did in the last couple of examples, we said, well, then dy over y would be equal to constant times t, and we know how to solve that. So let's try that out here. Let's try a statement right here. Let's see how this works out. Let's say that we're told that the rate of change of p, some variable p is with respect to time t, is proportional to 25 minus t. How would that work out? Well, okay, just like we said, we're saying that the rate of change of variable p with respect to time t is equal to a constant times the quantity 25 minus t. All right. Well, our separation of variables would work right here. If we say it's proportional, well, then dp is going to be equal to k times 25 minus t dt. Okay. Well, now in this case, that works out this way. dp, if we take the integral on both sides, the integral of dp is equal to the integral of our constant times 25 minus t dt. And just like every other equation that we've been solving, then p is going to be equal to our constant times 25t minus 1 half t squared plus some other constant right here. We're going to use this as a different constant. So there's a constant right here. And actually now we've got two constants floating around in our variable equation. Nonetheless, this family of curves would be the type that would fit this description. Let me come back up to this one right here. We just said that if dy over dt is equal to k times y, then dy over y is equal to k times t. That's not a very good k, but but it works. Okay. So let me finish off our statement right here. What would that mean to us? Well, that would mean that we have the type of equation that goes like this: dy over y is equal to the integral of k times t dt, or k times dt. Well, I did a good one right there, right? That should have been dt, shouldn't it have been? Okay, correction made. So, what does that mean to us? Well, okay, if we take the integrals on both sides, we get the natural log of y, and let's assume that y is a positive value, is going to be equal to k times t plus a constant. All right? So y is going to be equal to e, raised to the k times t plus a constant. Well, going a little bit further right here, this would mean that y would equal to e to the k times t times e to the c by our exponents rule. Of course, e to the c is itself its own constant, so y is equal to c times e to the kt. So sort of an interesting observation right here is that if we have statements that involve rates of change proportional to itself, we're actually going to use this model right here, y equals ce to the kt as a solution. And it is perfectly verifiable that if you took the derivative of y with respect to t, and that would equal to a constant times y, well, we would certainly get an expression that this would certainly be a solution to when we verified our solutions from the last section. Okay, more to come.